Okay, that certainly brings back not very pleasant memories, but I'm going to record. Anyway, so yeah, so today we're going to do fork join parallelism. Um, yeah, so and again, I guess I should include the acknowledgement here. The fork join framework, a lot of the stuff is from Dan Grossman, who used it in his class at University of Washington. So, okay. Okay, so what's the idea for this lecture, right? So we have multiple cores on our computer, right? So if you have a dual core computer, that means you've got two cores. If you have a quad core computer, that means you have four cores, and so on. So what does that actually mean? Right? Those are nice buzzwords, but what does it actually mean? So the idea is a core is can run everything that the processor used to be able to run, right? Back in my day, we used to talk about in terms of processors. And so the processor would do all of the work. A core is essentially can do all of that stuff, but now you have more than one of them. Okay. And so your computer can actually run, two applications or four applications, or it can use multiple cores for a single application, right? And that's what we're going to be looking at today. Okay, and so we've kind of ignored this up to this point, right? So all of our programs have just assumed that we're going to do one thing at a time. Okay, and so that's sort of a good way to get started, but it's actually not using all of your computing resources, right? So your computer's got multiple cores. How do we actually program it so that we take advantage of that? Okay, and so in order to do that, we're going to have to split our program into multiple parts that can run on different cores at the same time. Okay, so we don't have any way of expressing that right now, but that's where we're going to go. Okay, so I'm going to start with a little toy program here. So this is to sum an array, right? So we're going to take, there's a function here that takes an array and then a low and a high. And so the indices low and high are sort of which part of the array we want to sum up. Okay, so this is the kind of standard program. It's probably what you would write if I asked you to do this task, right? We're going to have a loop and it's going to go from the beginning to the end and it's going to add everything up into a running sum and then it returns that sum at the end. Okay, so this is it's sort of a trivial problem. I don't think you necessarily want to dwell on this problem a lot, but it's a program where we should be able to do stuff in parallel and we're going to use it as our example to motivate, oh, what can we do in parallel and how do we do it? Okay, and so the reason this is a good problem to work on is that there's a fair amount of stuff to do here, right? If the array is long, this is going to take a long time, and there the different parts seem like they should be able to be happen together, right? So if we were to split the array into different parts, then uh, one core could sum up the first part of the array, the other core could sum up the second part of the array, and then we'd be able to add up the results together. Okay, so that's why we're doing it. Okay, so here is a version of that problem, splitting it into two parts, right? So I have a left and a right, and so left and right are each calling simple sum, right? That's the code from the other slide, right? So the first part, the left part, is going to sum between low and high plus low divided by 2, right? So the average of high and low is going to be the middle of the array, right? That's the idea here. So we've got an array. Oops, where that line came from. So this is low down here. This is high. We're split it in half. And so this is the average, right? And so we're going to sum this part in left and we're going to sum this part in right. Okay. And then for right, is again, it's doing from the same place up to high, right? So note that the second index we're not actually using, right? And if you look back at simple sum here, right, we're going from low up to, but not including high, right? It's less than here, so it's not including high. And so these two halves exactly cover all of low to high. And if simple sum works, right, it's the code on the previous slide, we'll get the two sums, and then my sum function here is going to return their actual sum, right? So that'll be the sum of all the values in the array, not just, but now we've done it in two kind of separable parts. Okay, so great. That still doesn't actually run anything in parallel. So how do I tell the program or the computer, oh, these two things I want you to run on different cores? Okay, so we're going to do a little bit of cheating here. So conceptually, we're going to use these new keywords fork and join. Let me emphasize these are not actual Java keywords, right? So you cannot type this in and actually have it work in Java. We're going to talk about uh, forking and joining. Later on, I'll show you the actual Java code. The reason I'm not showing you that now is that the syntax is not very pretty. You'll see. Hopefully you believe me. Oh yeah, it was really nice to have fork and join. But the idea here is once you understand where you want to do a fork and join, then it's not that big a step to say, oh, I just have to put it in this funny syntax that doesn't necessarily make as much sense. Okay, so again, we're just doing it the simple version here. But yeah, so that we have the first keyword here, fork. So fork basically says, oh, this task here, the rest of the line, that's something you can run in parallel with the main thing you're doing, right? So we have the main strand that we're doing is going to run this function, the sum function. And oh, by the way, fork here creates it's called a child strand, child thread, and says, oh, I want you to run simple sum. Okay, and then I will continue on and do simple sum for the right side. Okay, so that's what fork does. It basically says, oh, this part you can run separately. And then join at the bottom there says, oh, now I need to actually wait, right? Because what I don't want to try to do is return left plus right, this last line here. I don't want to try to do that until both left and right are done. Okay, and so it's possible that the second half here, right gets finished before left. Okay, and if that happens, and I try to do the sum, I'm going to get the wrong answer. Okay, so I need to wait until the left part is done. Okay, and so that's what join does. Okay, so fork says, oh, this part you can run separately, and then join says, okay, I've got to wait for all the separate parts to come back together. Okay, okay, good. Okay, so what am I trying to do here, right? This is a little graph where time is on the x-axis, right? So my program used to start here and run to the end. Well, I still need to do that amount of work, but hopefully now I've split it into two parts, right? So the first part is going to run the top, right? It's going to take that long. The second part is going to run on the bottom. That's going to take that long. And they both finish early, right? They finish earlier than they would have if one core had been doing all of the work, right? So I'm using two cores. Each core is working half as long, and then it's going to finish much faster, ideally in half the time. Okay, so that's kind of the pictorial approach of what I want. Okay, so here's a different portrayal of what fork and join are. So in our normal picture, right, our normal code looks like this: A, B, C, D, E, or A, B, C, D, right? Those are function calls that we're making. And I can depict how that runs actually as well. I'm going to do A, right? That's this first box. Boxes are called strands, right? So this is a chunk of code we want to run without a fork or join, right? It doesn't include any forks or joins. I'm just running this code. Boom, finish A. And then there's an arrow and then B, right? So the arrow here means, oh, the top thing has to finish before B, right? So A has to finish before B. Okay, once A is done, then B is able to run and I'll run B. And then once B is done, we can run C. And once C is done, we can run D. Right. So we've got these four lines, they all have to run in order. Right. So the arrows here are these precedence constraints. They're showing the relationships between different strands. And so the relationships aren't very interesting at this point because there's no forks and joins, right? It's the whole program is one big long chain. Right? That's the sort of the simple kind of program. Once you add fork and join, it gets a little more interesting, right? So here's the same program, but I've added some forks and joins. Okay. And so now, right, for example, B and C could run at the same time, right? Because B is marked with a fork that says, oh, you're allowed to run this strand separately from the main strand, right? So why do I have the precedence constraints that I have here, right? So A has to run before B and C, right? You're going to do A before you fork off B. And so you can't start B until it's forked into a separate strand. So A has got to finish before B. A's also got to finish before C, right? Because it's just A something and then C, right? So just they're both sort of serial execution things. We're going to run, them in order. Okay, and so A's got to run before B and C. B and C can actually run in either order, right? Because I could, as soon as I mark B separate, oh yeah, this is something you run in separate strands. I could just run B right now. I could actually also just wait, right? I could, oh, it's marked as ready, but I kind of want to keep the main strand going, and so I'm going to go to C. Okay, so those could happen in either order, right? That's what it means to be kind of next to each other in this diagram. There's no precedence relationship between those two. But then both of them have to finish before D, right? So C's got to finish before D because C comes before D in the straight line code, and it's not forked or anything. And B has to finish before D can start because of this join, right? This join says, oh, I'm going to wait for B to finish, right? And any other strands that I forked off, but in this case, just B. Okay, and so we're going to run A, we're going to run B and C in some order, possibly together at the same time, and then we're going to run D. Okay, so that's what that sort of picture means. Now let's actually look at what happens, for some code, right? What happens when we apply this to code? Right, so in this code, right, I've got printing one, forking printing one, then printing two, forking printing three, the join, and then forking printing four. So here's possible things I could print. Which of those is actually going to happen? Okay, and so at this point in a real lecture, I would stop and we'd run the clickers and students would vote. Normally, what I would do is they vote. I kind of look at the results, assuming they didn't like all get it or all completely miss it. I would then have them discuss in small groups and then vote again. Okay, after they voted again, then we'll talk about the answer, right? So I'll show them the answer. That's the next slide. And then we'll discuss it and the other choices. So that's kind of what I'm going to model in the video. I'm not actually going to pause and have you guys answer. I will like maybe put in a brief pause. So what I do when I'm doing this as an online lecture, I will remind them, oh, you should pause your video now and figure out your answer, right? Because again, the pedagogy is basically you want to be thinking about the problem instead of just watching me talk. And so you can do that just by pausing the video and figuring out the answer. I'm not sure that students actually do it very much, but I think they should, right? I think it's a good, I think it's a better use of their time than just watching the lecture, right? So I don't know, and I encourage you to do it too, for the same reason, right? But anyway, so that's the pedagogy. Which of these is possible? Oh, it turns out that only number two is possible, right? So how can that happen on the printing? Do I? Yeah, so here's the precedence diagram for this code, right? What happens? Well, one is happening, but that's on a separate thread than two, right? So there's no relationship between one and two here. Then we're going to fork off three. So two has to happen before three. And then there's a join. And the join is basically one and three coming together. And that's going to happen before four. Right. So that's the precedence diagram that comes out of this. Okay. And so I think it's helpful to have the precedence diagram. Maybe I actually we should go through the answers and then draw that diagram. That's probably actually a better way. But anyway, so how is two possible, right? So let's start with the correct answer. 2, 1, 3, 4. Well, this fork here doesn't mean you have to start one. It just means you're able to start one. So suppose that I'm a little slow starting printing one. I'm going to print two first, right? So print two, and then, oh, I'm allowed to print three. I'm not required to print three, but I'm allowed. So one and three here could come in any order. And so for option two here, I'm going to do it one and then three, right? So those could be in either order, but I'm just picking the specific order. And then there's a join, right? So one, two, and three all have to be printed by the end of this join, by the time the join finishes, right? And then I print four. And so that's why you get this four here. Okay, and you can see the same thing with the picture, right? So what could happen? Well, I'm going to do the two, then the one, right? Those are independent. Then I'll do the three and the four, and that's going to respect all of its precedence constraints. Okay, why can't I do 1? Right? Well, 3 can't print at the very beginning, right? Because before 3 is allowed to print, right? This is the line that enables 3 to print. That doesn't run until 2 is already printed. Okay, so you can't have 3 before 2 in this case, right? So 1's not possible. What about line 3 here? Um, 1, 2, 4, 3. So here we have 4 printing before 3. That's not allowed either because this join here is going to force 3 to have printed, right? We're going to wait until 3 prints, then we're going to go on and print 4. And so you can't have line 3 here because the 4 prints before the 3. Okay, so good. What about this scenario? It's a different one, but same kind of idea. Okay. And so again, figure it out. Which of these is possible? Turns out 1 and 3 are possible. So, right, so how can 1 happen? Well, I have to print 1 first, right? Then I have the option of printing 2, and I said, yeah, let's do that, right? So two is fast off the gate and immediately prints, and then 3 and then 4, and then the join, nothing's gonna happen there, right? It's already finished 2. There's nothing to wait for. So 1 is definitely possible just by straight down. 3 is also possible, right? We're going to do 1 on this first line, but then, oh, this fork, I'm not obligated to print the 2 right away. I'm going to print the 3, and then I'll come back to the 2, right? So the 2 is available to print, but it doesn't have to print right away. And so in order to have this message, version 3 printed, um, the 2 is a little bit slow off the draw, and it is beaten by the 3, but not the 4. Okay, so what's the problem with number 2 here? This one's not possible. This one's not possible because the 2 is actually beating the 1, right? The 1 has to print before we fork off the 2, and therefore the 1 has to print before the 2. So it doesn't in II here, and so that doesn't work. Okay. And again, you can draw the precedence diagram for this. See if I can. Oh, there we go. Look at that. So we have 1. Then we're going to fork off the 2, and then 3, and then 4, right? So the top row here is just the straight line code, 1, 3, 4. After the 1, we have the option of printing the 2 at any time. And then we do the join, right? So the join here is after the 4, right? Nothing happens. It's kind of an awkward diagram because I should have a 5 here to print, but I didn't put that. So, here's the diagram with the rest of the program being after that join. Okay. Okay. Oh, oops, not there. Okay. So that's our fork and join. How do we actually go back to our simple sum and let's use a different number of cores, right? So I gave the answer with 2 cores, right? Here's the 2 core answer, right? The overall sum is going to be 2 simple sum calls, once for the first half, once for the second half, and then do the join. Okay, so down back here, oops, using a different number of cores, what can I do? So the one on the left is with 3 cores. And so how do I do that? Well, instead of splitting first half, second half, I'm going to have 3 parts. The first third, the middle third, and the last third. Right? And so, again, here's my diagram. I'm going to have my array, and I'm split it into 3 parts. Right? And so this is low, this is high. Right? P1 is high plus 2 lows. That's going to be right here. P2 is going to be this one. Is 2 highs and a low, right? The average. And then so the simple sum here, S1 is going to be from low to P1. This S2 is going to be P1 to P2, sum of that part, and S3 is going to be the sum of P2 to high. So S3. Right. So I've broken the array into 3 parts. Compute their sums. and join and then return the sum. Okay. Notice here again, I'm using a fork, right? So I figure out the indices. I use my fork to say, oh, I want to do the first third potentially at the same time as other stuff. Oh, I want to do the second third potentially the same time as other stuff. And then my main strand is actually going to take care of, or my main core is going to take care of the last part, right? And then we wait for everybody to finish and then we sum. Okay, so the version over here on the right, this is splitting into four parts, right? So the picture's pretty much the same. Oops, I don't even have to redraw. There we go. And we're splitting it into four parts now. Okay. And these are the P1 through P3 are these indices in the middle. Right? P1, P2, P3. And then the sums are S1, S2, S3, and S4. I join and then I return the overall sum. Right. So this is definitely getting a little painful. How do I do it for a generic number of cores? Right, here's code that does that. Right, so I have C is the number of cores. I'm presuming here that I have some magic function that's going to get me the number of cores. Okay, then I'm going to have an array of sums that I can, an array of the sums of each of those parts. Right, so I'm going to split the array into C parts, and then the sums here is going to contain the values of each of those parts. Okay, and then so then in a for loop, I figure out the indices. This is the left index for the ith part of C. This is the right index for the ith part of C. Um, I'm going to do my sum from S to E, right, and put the result into sums. And then that, you can go through the details there. That's going to actually create C separate strands, each doing one seat of the array, and putting the results into the sum array. Then I do join, right? Wait for everything to finish, and then I sum it all up, right? So here I'm using simple sum to sum up all of the subparts. Okay, so yuck, I guess is maybe your first reaction. This is not exactly beautiful, but it does actually create the right number of strands, right? And so this should work pretty well, provided all of the core, each core picks up a strand and runs that strand, and then combine the results afterwards. Okay, so again, for a really long array and a machine that's pretty idle, this is going to work pretty well, right? We're going to use all of our cores. We're going to get good performance. Okay, so why might that not happen? And I probably would, in an interactive class, I would, actually ask them and wait for an answer. But what if C is wrong, right? One thing that might happen is I get this number of cores, but that's not actually the number of cores I have. So the way functions like get num cores work is they tell you how many cores your machine has. That's different than how many cores the operating system is going to let you. Okay, so your machine might be 4 cores, but the operating system decides, oh yeah, I really need to do a background thing, or oh the user of this computer is also watching Netflix while they run this program, right? And that takes a whole core, right? And so I might not actually be getting as many cores as I think I have, right? It's not, I might not be getting the entire machine. Okay, and what's going to happen in that case? Well, you have some of the cores that do double duty, right? So this is a situation, I may have 3 cores, so I've split it into the 3 strands, but I only get to use 2 of them. And so, well, each of them gets one, but then there's this extra strand that's going to have to go somewhere, right? So the first core is going to get it, and then I'm not finishing on time, right? What I'd really like to have happen when I split into 3, whoops, is I'd like to have them all running at the same time, right? And so you finish here, right? But if I have to wait for 2 things to finish, you don't finish till out here, right? It's taking kind of twice as long as it should. I have to wait for 2 strands to finish on a single core, not just one. Okay. And so it doesn't help, I'm idle here, but I don't have useful work to do there, at least not for this program, right? Because I've only got 3 strands. Okay. And so this is a case where if you're wrong about the number of cores, right? Specifically, if you think that there's more cores than you actually have access to, your program's going to take longer than it ideally should, right? I don't necessarily want the machine's number of cores. I want the number of cores that I'm actually going to be able to get, right? Which you may not know, right? That's a unknowable thing when you ask, right? You don't know that the OS is about to start backups. And so how are you supposed to get the right information? Okay, the other thing that can go wrong, not so much for this program, but in general, is that what if the strands need different amounts of work, right? And so this is a situation where, oh, I have some problem. I've split it into two strands. I've tried to do it nicely, except that that's not what it ends up happening, right? So for whatever reason, the amount of work in the first strand is more. Okay, and so this can happen in an unpredictable way, right? Think again about a more complicated program than this little sum, right? Sum is very nice because we kind of know how long everything's going to take. But maybe I'm making a function call on the values in the array, and that function call might take different amounts of time depending on its arguments. And so I can't immediately tell, oh, this part's going to take longer than this part. And so if I split the array evenly, I'm going to end up with strands that require different amounts of work, and each one gets a core, but then I still have to wait for whichever strand is slowest. Okay, so again, this is going to make me wait longer than necessary, by virtue of not being able to split the work perfectly. If the work is split perfectly, I should be able to get C times as fast. But if it's not split well, then who knows what speed up I'm going to get. Okay, so again, that's a different kind of problem. And so these are both kind of hard to avoid, except it turns out there's a kind of a standard trick. Okay, and so here's another version of the program. It's actually simpler, and I claim that this is going to help us out. Okay, oops, why do I have a different color there? I should not have a different color there. Oh, it shouldn't be underlined either. Now that you mention it. Okay, so what does this version of sum do? Right, it's using recursion, right? And so, well, my base case is the array is just one value. Just return the one value. Done. Okay, that's easy. Otherwise, I'm going to split the array into two pieces, right? A left half and a right half. And I'm going to do a fork on the left half, but note here, unlike the other code, I'm actually calling sum, right? So I'm not calling simple sum. This is the method calling its actual self. Okay, so what's going to happen when I call sum here? Well, it's also going to split the array recursively, and I'm going to get lots and lots of parts. Right, that's the idea. Right, and so left and right both call the original sum routine, which is going to recursively split the array. Then I'm going to join them and then get left and right. Right. So again, what am I doing here? Right, I have the whole array. I split it up into two parts, right, left and right. Right, how do I run the left part? Well, the left part is also going to be recursive. Right, the right part is also going to be recursive. Right, adding a little space here for separation. Okay, and again, how do I do the left part of this one? Right, it's going to split in the halves. Right, same thing over here. Right, so I end up with a very large number of strands, potentially down to the number of strands equals the size of the array. It turns out that's too many, and we'll come back to that later. But conceptually, you can think about it as just creating a very large number of strands, right? Many more than the number of cores. Okay, and so that's great. Why does that actually help me? Okay, actually, let me go to the next slide here. Oops. Okay, many more strands than cores. And so the idea here is that when a core finishes a strand, it takes another one. Okay, and so what happens if you've got two cores? Right, clear this up. Right. Well, they both start with a strand. When they finish it, they both get another one. They both get another one, and so on. Right. Oh, that's pretty good. Right. That's kind of the ideal behavior. Right? What happens if I have three cores? Well, they each get a strand. right? When they finish it, they each take another one. Right? When they finish that one, they each take another one, right? And again, I'm getting a perfect load balancing here, right? And the load balance didn't depend on knowing the number of cores, right? The two core version got perfect load balancing. The three core version got perfect load balancing, right? Or close to perfect, right? Um, I guess you can get one more strand, right? If you have an odd number of strands in the top case, right? One of the cores is going to do one more strand than the other one, right? Same thing down here, right? You can have one more strand worth of work on one of the cores or two of the cores, okay? But no matter how many cores you actually get, um, you're going to get very close to perfect load balancing, okay? And the idea here is that, again, these strands are very small, and so being off by one is okay, right? You're going to still get a good load balance, right? Because my load balance doesn't depend on, or the algorithm that I'm running doesn't depend on the number of cores, right? Nowhere in this code am I asking about the number of cores. Then it's going to work just as well for any number of cores, right? So we're not using that information, so that information being wrong doesn't matter, right? I'm going to end up with a good load balance. What about in the second situation where the strands require different amounts of work? Well, suppose my first core here gets a really long strand, a really big strand, and then the second one gets a small one. Okay, that's okay because when the second core finishes, it'll just take another strand, right? And nope, the first core is still busy. Second core finishes, it'll take another strand, and so on, right? So you still can get a bad load balancing, but it's a lot harder here, right? Because the idea is if your core is working on easier strands, right? If your core finishes strands sooner, then you just take more, right? And so if you get stuck doing a really long strand, that's okay. You'll just take fewer strands. And so it sort of naturally moves work toward the strands that are less busy. Um, and again, achieves a good load balance, even though you have no idea when you start a strand how long it's going to take. Right? Again, the algorithm here doesn't depend on knowing how long the strands are going to take. It just depends on, well, I finished one, I'll just take the next one. Right? And again, you're assuming that you have a large number of them, and so each strand is relatively small, and so the little bit of imbalance at the end here is not going to be very big as a portion of the entire job. Okay. And then this bottom line here is just little terminology, right? So when you create a strand in many systems, it actually sort of has a core that it's assigned to, right? But later on, it can change that, right? So if a core runs out of strands, it can do what's called work stealing, right? It goes to another core and steals one of its strands, right? So that's an implementation detail that's useful for implementing this efficiently. Um, but for our purposes, it doesn't really matter, right? Which is the key thing is just that um, faster cores end up doing more strands. Okay. Okay. Boom. Okay. So recursion is my friend. Uh, Backing up a little bit from that, what's my running model here, right? So I've implicitly been assuming, oh, how am I going to run my strands, right? If you get the precedence graph, what happens? Okay, so our assumption for the machine is we have a pool of cores, processors, or threads. Those are different terms for, I don't know, related things. I shouldn't say they're the same, but they're related things. Um, the way I've been explaining in this lecture, they're cores, right? So I have multiple cores on my machine. I'm just going to, from now on, I'm going to try to call them processors. Right? Processors is the historical term. Again, in the olden days, we didn't have multi-core machines, and so we could have multiple processor machines. Nowadays, everything's multi-core, and so the cores are effectively taking the role of old-time processors. Okay, so we have a pool of processors that are available to run strands. Each time unit strands without unfinished predecessors are assigned to available processors and completed. Right, and so again, if you have a picture here, um, I've got some precedence graphs. right? So this strand here is not available to run, right? But, A and B here are, right? So those will be assigned to run, right? And then that will satisfy these precedence constraints, and now later X will be able to run. So I'm looking for strands that don't have unfinished predecessors, right? Where I've finished all the predecessors, right? I've met the precedence constraints. Those are the ones I'm going to assign. And so basically, those strands are going to get assigned, and we're gonna run them and finish them. Okay. Despite what I've been talking about, right? We're normally going to assume each strand is an equal amount of work. You don't fully need that assumption, but it simplifies all the examples, and so we're gonna make that. And then how are you assigning uh, the strands to processors? Well, we're just going to use this rule. Processors are never voluntarily idle, right? So processors might become idle, right? If there's not enough strands for them to do, or not enough strands whose predecessors have been finished for them to do, then they might just have to hang out, right? There's nothing for them to work on. They're just going to like go to sleep or wait. Um, but they're never going to just hang out on purpose, right? If there's work to be done, they're going to chip in and try to do that work. Okay, so there's different ways to assign strands to processors, right? They are going to give different amounts of time required in some cases, um, but that's okay, right? We're looking at uh, how well the system is going to work just under this rule that, well, we're never voluntarily idle. Right? So it's kind of a greedy algorithm. Okay, so here's my little example, right? So A, B, C, D. Here's the precedence graph. Processor one, right at the very beginning of time, it's going to grab A. Okay. At that same unit of time, processor two is just going to be idle, right? There's nothing else it can do, right? A is running, can't run that, but then B and C and D have precedence constraints that haven't yet been met. Okay, so that just has to hang out. Oops. Okay, but then at the next time unit, A is done. Now B and C are both available, right? They all of their precedence constraints have been met, and so those two are going to run, right? One and two both take one of them and run. Okay. And then the next time unit after that, right, B and C are done. So now D is available. And so processor one grabs that. Okay. And so this is not the only mapping. You could switch A to run down here instead, or B to run down here instead. Those would be valid mappings. But you're going to have A running first, then B and C, and then D. Right? It has to be that because A is the only thing that can run initially. B and C can both run, and they have to both run, right? Because we're not allowed to keep processors idle voluntarily, right? If there's work to do, you got to work on it. And those are the only two things to run, right? So they're going to both run. And then D will have to run in the next unit, right? Because again, you can't keep it voluntarily idle. Okay. So that's the example. Let's actually do this for you. Right. So how long will this graph? So here's a graph with A through F. How long will this take to run? Right. So 3 units, 4 units, 3 or 4 units, 4 or 5, and so on. Okay. So how long will that take? Slides here. It's going to take either 4 or 5 units. Okay. So how can this be? Okay. So we have to come up with schedules for 4 and 5. Okay. And again, the students will do this for you in practice. Right. So I've got two processors, right? So there's this one and this one. Right. So the first time unit A is going to run, and that's the only thing, right? I have to do that. Okay. So it turns out, so if I want to run in 4 time units, it's very important that I do this part over here. Right. So I'm going to make sure I do that. B in time unit 2. And then processor 2, it's got to do either C or D, right? It can't run E or F, but C and D are both available. Okay. And then processor 1 is going to do E. And then processor 2, its only choice is D. And then processor 1 will do F. Right, and that's my 4 time unit schedule. Okay, so that'll take 4 time units. If I want a 5 time unit schedule to see that that's possible, ready at A has to run all by itself the first time unit, but now maybe I'll do C and D. in the second time unit. Right. So those are both valid choices, right? They're all of their predecessors have been run. So sure, we are allowed to run those. But now I'm left with B, E, and F, and those have to run one at a time, right? Because they're precedence constraints with each other, right? So, for example, it could run B, E, F, or the same thing on the first processor. But anyway, here's a schedule. This gets you 5, and this is also a legal schedule following our rules. And so here's a schedule that gives you 4. Here's a schedule that gives you 5. Those are the only two possible values. Okay, I guess you can't finish it in 3 um, because there's a chain here, which I guess I shouldn't show this to the students, though the one of the goals here is to have them realize, oh, this chain's important. And you can't take at least you can't take 6 or more. Why is that? Basically, you can't stall on working on this chain any longer than you can stall one time unit by doing C and D, but after that you have to keep working on the long chain, right? And so that only gets you up to 5 and not 6. So again, actually, probably don't do that in class because we're gonna come back to that and see it again. Okay, so when I did this in class, there were actually a lot of questions about it. Hopefully, I fixed the slides so that um, there will be fewer now, but you know, your mileage may vary. Okay. Okay. So what about this one? So this is another problem. This was actually on the second day of the lecture, right? So we've done what took me a full day of class to get to. And so the first day, like I said, there were a lot of questions on that last graph. And so, um, the second day, I sort of did a little review of the terminology and tried to, answer the remaining questions. And then I came to this one. So, this is now that you understand it, let's actually use our new understanding. And so let me plug in here. I'm about to lose my display. Okay. So again, have them do this and then see what the answer is. Oops. Come on. There we go. So it turns out you could do 5, 6, or 7. And so I like to do none of the above. Oh, I guess I say in the notes here, you could potentially skip this one. Again, it depends if they're having trouble or not, right? There's no point in doing extra questions. But if you need to, then it's available. Okay, so you can do this in 5, 6, or 7. And so what's the fastest we can finish? Well, we can't finish in 4 actually because of this long chain. Right? So A, B, E, H, I. You can't, those have to do one at a time. Okay, and so you have to take at least 5 units of time because that chain is linked 5. Okay, so that's kind of an important realization. That's going to prevent you from doing anything less than 5. Clear this up. How can we do it in 5? Well, I'm going to do A, and then actually I'll just do the schedule here. A, B, E, H, I. Right, so I want to try to finish that in 5 units. That's my first processor. Like it's busy the whole time. For the second processor, well, it can't do anything the first time unit because A has to finish first. But then I've got these 4 strands to finish, and I've got 4 remaining units of time. And so it turns out you can just plop them down, right? So D has to come before F and G, but not hard to do. Okay, so there's a schedule that uses 5 time units. Okay, what about 6 time units? I put this in the notes. You can do A, and then we're going to do C and D, right? So we're going to stall working on the long chain by doing this other stuff. Right, so again, A has to come first, but then we're going to do C and D, and then we'll get back and do the long chain. So B, E, H, I, right? So that's our 6 time units. And now the second core is going to finish up, right? So I've done D, now I need to do F and G. Okay, so that takes 6 time units. You can't do I here because you have to wait for H to do it first. Okay, so that's the 6 time unit schedule for 7, that I didn't originally think was possible. Do A, right? Again, A has to go first. Then let's do C and D, right? Same as before. Now let's do F and G. Right. So again, this is a legal schedule, right? We're doing things rightmost, and we're picking the rightmost available job. Right. So we've spent 3 units of time. Now we still have to do this 4 unit sequence. Right. So however, you can put it in lots of different ways, but whatever you do, you need 4 units of time to finish those strands. Right. And so that works out to be 7 total units of time for the whole schedule. Okay. You can't go any slower than this. Um, yeah, and so the reason I gave was basically if you look at everything except the long chain, right? So C, D, F, and G, right? You have to finish that within 3 units of time, right? If you're not working on the long chain, you can waste at most 3 units of time, right? Because you do A, and then C and D, and then F and G. Okay, and so that gives you 3 units of time that aren't spent on B through I. And you can mix them up, but that's that's the longest you can take. Okay, so I think I'm going to actually stop here. Oh no, this one. Oh, here's another example. Right. So again, um, this might be too much. This example is we're showing now there's not a long chain, but there's just a lot of tasks, right? So here we're kind of emphasizing, oh, the long chains are important, like long chains, long chains, long chains. Now, well, what if we don't have a really long chain, right? So I have a chain, but basically I have a lot of strands, right? So what's that going to take? Well, it's going to take 5 or 6 time units again, even though the longest chain is only length 3. Okay, so what could happen here? Find my painter here. Oh, okay. So how do I do this in 5? Well, again, got to run A first, right? Can't do anything other than that. Um, I think I don't have to be that careful here. So I'm going to do B and C, and then I'll do F and D, and then I'll do E and G, and then I can do H and I. All right, so that gets me 5 units of time, no problem. To get 6, right, again, I'm going to start with A. Um, and then, like cheat sheet here. Let's do D and E. Right. So the idea here is I've got work. I'm going to leave C and F for the end. Right. That's going to be the last thing I do, and I'm going to make it so that one of the processors is going to be idle while the other one works on those two. Right. So I'm unlocking a lot of work here. Okay. So now I've got B, C, which I'm saving, G, H, and I. Okay. Well, let's do that, but let's save C. So we're going to do B and G, H and I. Right, so that's a valid schedule. I've used 4 units of time. Now I still have C and F left. So whatever I do, wherever I put it, it's going to use 2 more units of time, and that's going to take 6. Okay, so the idea with these is we've sort of seen what can happen. And so this is what happens when there's lots, right? Your time is kind of largely determined by the number of tasks, but with some, the precedence constraints still matter, but mainly emphasizing the number of tasks. The other one is emphasizing the depth. Okay, and so let me actually, I'm going to stop it there. I will make a separate recording.